Hello, Chemistry. The intention with this video is to help you with your corrections for Test 9 by solving problems similar to those that you saw on the test. As we discussed in class, your performance on that test was disappointing. But if you do your corrections, continue to show diligence with homework and labs, your failure will be a good learning experience and won't impact your grade too much. One of the reasons that so many of you struggled with that test was that it contained word problems which required critical thinking. I told you to expect those problems. I gave you several examples on the study sheet that I handed you in class, but you struggled. And understandably, because those are difficult problems. I think the style of problem might be new to many of you. You might be used to being just handed an equation and told what values to plug in and calculate yourself to an answer. But I want you to move beyond that. Frankly, we can build computer programs that can calculate better than you. We could build a computer program that can plug and chug chemical calculations much more efficiently. But I'm not trying to turn you into a bunch of calculators. That would be a waste of time and a waste of your potential. I'm working to help you to learn how to think effectively, to help you develop the mental skill set that would let you build a calculator. The picture we're looking at is a good example of how someone did that. I was just thinking about this. This is a picture of a solar eclipse where the moon traverses in front of the sun during daylight on Earth, such that the sun is obscured, but just barely. You'll notice that the corona of the sun is coming out from behind the moon, but the moon is just the perfect size to obscure the main disk of the sun. This beautiful phenomenon, we had one in Arizona a couple of years ago, is only possible because the moon is 400 times smaller than the sun and also about 400 times farther away from the sun. If I believed in coincidences, I would say that was a stunning coincidence. There are 8 planets and a couple hundred moons in the solar system, but there is only one place where the mathematical ratios allow an eclipse like this. And it happens to be the only place where there are observers to be thankful for it. It's pretty interesting. So the photo itself was taken about 100 years ago during an experiment conducted by Albert Einstein. And believe it or not, this photo proves that gravity bends light and establishes the framework for what we now call general relativity. If you guys are interested in how Einstein did that and the nature of the experiment, we can talk more about that in class. But I'm showing you this picture because I want you to understand that nobody gave Einstein a bunch of equations. There was no textbook that he could look in the back for answers to. Nobody told him what values to use. He had to carefully think about the concepts that were involved in the problem he was trying to solve. He had to decide what mathematical tools could be used to prove or disprove his theory. And this is not beyond you. You might not do it on the same scale as Albert Einstein, but if you are able to do real problem solving, then you'll be able to make meaningful contributions to human knowledge. And that is what God intends us to do, to love him with our entire mind, that we know his creation better. So let's begin. So let's start with problems 1 through 4. These are really pretty simple as long as you understand the concepts involved. Looking at problem 1, this is a slight alteration from your test, but it's going to show you the same concept. What is the mass of 1 mole? So when we're problem solving, we think, what do we have and what do we need? Well, we have the mass of 1 mole of C2H2. We know what we're looking for. We know the units that it has to be in mass. That tells us that our answer needs to be in grams. We have a periodic table. And hopefully on your note card, you have what a mole is. If you need a refresher, 1 mole is 6.022 times 10 to the 23rd of something, whatever it is. So 1 mole of oxygen is that many atoms of oxygen. 1 mole of O2, diatomic oxygen, is that many molecules of O2. 1 mole of potatoes is that many potatoes. So 1 mole of C2H2 is that many molecules, Avogadro's number, 10.022 times 10 to the 23rd. In case you're wondering what that would look like if we wrote it out. believe it's going to be that. Now, I might have missed a 0 in there. 1 mole of C2H2 is this many molecules of C2H2. Our question is, what is the mass of this many molecules of C2H2? And if you look at your periodic table, that number right below the atomic symbol is going to show you what the mass of 1 mole of each of those elements is. So our C2H2 is composed of 2 atoms of carbon and 2 atoms of hydrogen. The periodic table tells us that 1 mole of carbon has a mass of 12 grams, and 1 mole of hydrogen has a mass of 1 gram. If we add these up, 12 plus 12 is 24, plus 1 is 26. There are 26 grams of mass in 1 mole of C2H2. And I'm just getting these numbers, your grams per mole, off the periodic table. So your answer is going to be 26 grams. Now our next question, which has the greater mass, 1 mole of potassium chloride or 1 mole of table salt, and why? Now this requires some critical thinking. Okay, what is potassium chloride? Well, we've learned the naming convention, but there's another way you might get there, and that's simply that there's a term that's in common use, sodium chloride, which is table salt. And let me erase we'll work over here. You guys know that sodium chloride is table salt, NaCl. Potassium chloride then is potassium table salt. We're going to replace the sodium with potassium, KCl. That's potassium chloride. And our question is, which has the greater mass, 1 mole of potassium chloride or 1 mole of table salt? So let's think about, what do we have? What do we have? And what do we need? Well, we need to know the mass, the greater mass between KCl and NaCl. What do we have available to us? Well, we know what a mole is. We know what a mole is. 6.022 times 10 to the 23rd. We can find the mass. We can find the mass of a mole of NaCl and KCl using the molar mass from the periodic table. So once we find those two masses, then we just compare and figure out which one is greater. Then let's think about the why piece. We'll think about how we can answer the why question. This is the same problem-solving procedure I've been teaching you before. Start by listing what you have and what you need, and think about how you can build a bridge between what you have and what you need. So let's figure some stuff out. What is the mass of 1 mole of sodium chloride? Take a minute and get my periodic table here. Okay, well, we need the mass of potassium, we need the mass of sodium, we're going to need the mass of chlorine. They both have chlorine, though. So the mass of potassium, per the periodic table, 1 mole of potassium is 39.0983 grams. We're not really given significant digits here, so I'm just going to write out as much as we have. 39.0983 0.0983 grams per mole. The mass of sodium per your periodic table is pretty close to potassium, 22. I'm going to go ahead and make these 5 significant digits. 22.989, 22.989 grams per mole, and chlorine, 35.453. 35.453 grams per mole. Let's build up some molecules and see what their mass is. What these numbers mean is that every mole of potassium, for example, weighs just over 39 grams. Every mole of chlorine, every set of this much chlorine, has a mass of almost 35.5 grams. So let's build up some molecules. What's the mass of KCl? Well, it's going to be the mass of K, which is 39.099, plus the mass of Cl, which is 35.453. And that's going to get us 74.552. 74.552 grams. Grams per mole of KCl. All right, let's do sodium chloride, NaCl. Well, our sodium is 22.989, and I'm betting that a lot of you are already seeing what the answer is going to be. Chlorine is the same, 35.453. That's going to get us 58.442 grams per mole. So the first part of our answer is, which has the greater mass, 1 mole of potassium chloride or 1 mole of table salt? Well, clearly 1 mole of potassium chloride. So we can put that there. Now let's think about why. Why is that the case? There's a lot of right answers here, but I want you to demonstrate to me that you understand some of the concepts involved. One thing to notice right off the bat is that both KCl and NaCl share a common chlorine atom. So they share a common chlorine atom. Their difference in mass is going to depend on the difference between potassium and sodium in mass. If you look at your periodic table with me, you'll see that potassium is lower on the periodic table than sodium. That suggests that it's going to have greater mass. It's a larger atom. Potassium has 19 protons, whereas sodium has 11 protons. So an answer to the question why might simply be that a K atom has more mass than an Na atom. There are other right answers, but something that demonstrates to me that you understand the idea of arrangement on the periodic table, the significance of the mass of the atom in terms of the larger molar mass. Now, how many kittens are in 1 mole of kittens? Well, if you understand the concept of a mole, 1 mole of kittens is 6.022 times 10 to the 23rd of kittens. Pretty straightforward. Got to throw a unit on there and a box around it. How many whiskers are in 1 mole of kittens if each animal has 12 whiskers? Well, 1 mole of kittens is this many kittens. And just for fun, this time I'm going to do it without scientific notation again. So 1 mole, let's start with 1 mole of kittens. That is 6022. There's a decimal place there. 1, 2, 3, 20 more zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1 mole of kittens is that many kittens. We established that in the other problem. And if each one of those kittens has 12 whiskers, then the answer is simply 12 times that number. And then you do need units. Their unit is whiskers here. Pretty straightforward. You could do that in scientific notation if you wanted to be a little cleaner. Lastly, let's do the ordering. Think about what do you have and what do you need. Order the following samples according to their number of atoms. So I have these samples. I know their chemical formula. That's going to be useful. I know how much of each one I have because I know what a mole is. What I need to know is their order in the number of atoms. In other words, how many atoms is in each one of these samples? Well, let's start by answering that question. 1 mole of gold, Au, is that many atoms of Au. So 1 mole of gold, we'll just go ahead and write that, 6.022 times 10 to the 23rd atoms. Okay, simple enough. 1 mole of BaCl2, that's more interesting. Every BaCl2 molecule contains 1 Ba, 1 Cl, and another Cl. That means every one of these molecules contains 3 atoms. Every one of those molecules contains 3 atoms. And there is 1 mole of those molecules. So we could write it like this. That many atoms times Avogadro's number. And that many atoms is, of course, 3 atoms. If you wanted to, you could add up the subscripts to get that too. Remember, there's a ghost subscript of 1 under Ba right here. Anything that doesn't have a subscript has a 1. And then a subscript of 2. 1 plus 2 is 3. 3 atoms in this molecule. 3 atoms in 1 mole of that molecule. So the answer there for how many atoms is 3 times Avogadro's number. Then lastly, we're going to apply similar principles to O2. O2 has 2 atoms, 2 oxygens. So there are 2 atoms in 1 mole of oxygen. But if you look carefully, I'm not asking for 1 mole. I'm asking for 1/4 mole, 0.25. Now you could do this all in your scientific calculator, but hopefully already you're seeing the answers. Your mole of gold is definitely going to be less than your mole of BaCl2 in terms of atoms. And as is your oxygen too. So certainly this middle one, here's how I did it. You can do it however you want. I just labeled them A, B, and C. One way to think about this, 0.25 times 2 times 6.022 times 10 to the 23rd. Just start by doing that first set of multiplication there. 0.25 times 2 is 0.5. So this is going to be a half a mole. So our C, our oxygen, is the least number of atoms. It has 1/2 a mole's worth of oxygen atoms. Notice the math there. I'm asking you for a 1/4 mole, 0.25 moles of O2. There's 2 atoms in each molecule of O2. That's where I got the 2. And the problem gives you the 1/4, 0.25. 0.25 times 2 is 0.5. So our least is going to be C. Let me just say from least to greatest. It's going to be C. And then A. And then B. Okay. Problems 1 through 4. Let's move on. Picking up with problem 5, this is an empirical formula, finding the empirical formula by the percent of mass. In this case, our sample is 87.5% nitrogen and 12.5% hydrogen. I already did some of the preliminary work here. That's a mistake. That should say hydrogen or nitrogen, not carbon. So, basic problem solving approach. What do I have and what do I need? I have a percent by mass sample and I need an empirical formula. Now I would recommend, if you struggle with this on your card, make yourself a flow chart. There are several good ones in the book that show you, based on what you have, how to get to what you need. The basic procedure for this kind of problem is assume a 100-gram sample, find the molar amounts, and then use the molar ratios as subscripts for the empirical formula, and simplify as needed all through all that. So what do I have? I have percent by mass. That means I can make my mass whatever I want it to be. I'm going to assume a 100-gram sample. You could assume whatever you want, but 100 grams makes it easy to do the math. A 100-gram sample of my vitamin X contains 87.5 grams of nitrogen and 12.5 grams of hydrogen. I look at my periodic table to find out what the molar amounts are. The grams per mole for nitrogen is 14.01, and I have 85.7 grams. So the number of moles of nitrogen is going to be 6.2, we're going to call that 6.25. 6.25 moles of nitrogen. And if you look on your periodic table, you find that the grams per mole for hydrogen is 1.008. So 12.5 grams of hydrogen. I'm going to call that 12.4. 12.4. 12.4 moles of hydrogen. Now, what we can do is create subscripts based on our molar ratios. So we know that we have a molar ratio of 6.25 to 12.4. Because we can't have partial subscripts need to be whole numbers, we essentially just round. 6.25 nitrogen comes down to 6 nitrogen, and 12.4 hydrogen comes down to 12 hydrogen. Now there's a last step here. You're probably noticing, because this is an empirical formula, my subscripts need to be reduced as low as possible. And this is a 2-to-1 ratio here, so I can reduce this to NH2. And that is how we solve that one. That one is the kind of thing where it's going to be helpful to have a procedure in place. So I recommend I mean, this is just right out of the book, these kind of problems. I recommend writing the procedure on your note card briefly so that you know how to begin to tackle one of these problems. It really does hinge on the molar ratio. The molar ratio is the key to everything in stoichiometry. If you get that, then you're going to be able to move forward with a problem. That is problem 5. We're going to do one more. We're going to take some time and do one of the word problems, just one, and then that should equip you with some ways to move forward on the test. About this, and I hope you guys don't mind, but I'm just going to go ahead and do one of the problems from the test. I'm not trying to cheat you out of a challenge. If you want to give it a shot first, you can do that and then watch this video. But because you guys have struggled with this, I thought it would be helpful and encouraging to show you that it can be solved, and it really does not take that long. It takes way longer to explain, in fact. You operate a silver mine. Your mine produces silver ore in the form of AgNO3, and it also produces an excessive amount of zinc. Now, you don't need to know any of what I'm about to tell you to solve this problem, but this problem is built on a real-life scenario. AgNO3 is a common form of silver, but it's not very useful because the silver's wrapped up with a nitrogen and 3 oxygens. And very often, mines don't just produce one kind of mineral, they produce several kinds of minerals. So this mine is producing something that gives you AgNO3, and also you got all this zinc you need to find something to do with. And you realize that you can perform a single replacement reaction. I'm just reading the problem now. You can perform a single replacement reaction of your AgNO3 with your zinc and get pure silver. All right, so you have a process now. You can use one of the byproducts of your mine to refine your AgNO3 and get the silver that you're after. That's pretty cool. You have 200 kilograms of zinc and 250 kilograms of AgNO3. How much silver can you make by mass? And if you want to keep making silver, do you need more zinc or more AgNO3? Let's start by talking about what we have. And I have some of it written down already. We have our products and we have our reactants. A reaction is being described. What kind of reaction? Well, carefully read the problem. Mine the problem for clues. I gave you a few big ones in this problem. One of them is I straight up told you what kind of reaction you're looking for. You are looking for a single replacement reaction. A single replacement reaction with your AgNO3 and your zinc to form pure silver. So you have products, you have reactants, you have a description of the reaction. You know it's a single replacement reaction. I'm really giving you a lot of information. You have your periodic table. That means that you can find properties for silver and zinc and NO3 groups, things like that. You know it's a stoichiometry problem. You know that you are going to need, so start to think about what you need. You know because it's a stoichiometry problem, you're going to need a balanced equation. It's a limiting reactant problem, so you need to figure out which one you're going to run out of first. That's this part of the question right here. You want to keep making silver. Which are you going to run out of first? Do you need to get more zinc first or more AgNO3 first? And then how much silver can be produced? And read the problem carefully. The question is going to be, you have that much zinc, 200 kilograms, and 250 kilograms of AgNO3. How much silver can you make by mass? So our answer needs to be in mass. So we go ahead and write that down too so we don't forget it. You get a list of things that you have and things that you need. Now, we know it's a stoichiometry problem. Probably you're going to need some molar masses. So I went ahead and looked on my periodic table, and I figured out the molar masses for the various elements and compounds that are going to be in this reaction. Now, if you're curious about how to do this, review chapter 9 in the book, or check out the previous part of this video where we do it on the test. AgNO3, 1 mole of AgNO3, has a mass of 169.873 grams, 169.873 grams. Zinc, 65.38, etc. You can find all over the periodic table. I think you guys know how to do that. Now, let's start with a balanced equation. We need a balanced equation. That's the first thing on our list of stuff we need. So on one side of our equation, we have AgNO3 plus zinc And on the other side of our equation, we have, so it's a single replacement reaction. The other side of the equation, let's work out what we have. The problem tells us that it's going to form pure silver. So one of our products is going to be Ag. There's another product, though. There's got to be another product because everything coming into the equation goes out of the equation. So there's zinc over here, and there's the NO3 group. So it's a single replacement reaction. I've got Ag already. It must be that the zinc is replacing the silver. So my products are going to be silver and ZnNO3. So there we go. We have got the start of our equation. Now we need to think about how to balance it. The first step to balancing is to figure out how many atoms of each side of each type on each side you have. So on our reactant side, I have 1 silver, 1 nitrogen, 3 oxygen, and 1 zinc. On the product side, I have 1 silver, 1 nitrogen, 3 oxygen, and 1 zinc. Hey, you know what? This equation is already balanced. See how easy I am on you guys? I gave you already a balanced equation in your problem. You didn't even have to do anything weird. You just had to write this out, and you would have a balanced equation. Now, I do want to tell you that in the real world, because of some things that you haven't learned yet about NO3 groups and ions, this equation would take a little bit of a different form in nature. This does happen in the world. It would take a little bit of a different form, but it would still be a balanced equation, and this is also a balanced equation. So this is the one we're going to work with. So we have a balanced equation. Check. Now, let's talk about our molar ratios. Because it's a balanced equation, I'm going to go ahead and write down what we know our molar ratios to be. 1, 1, 1, and 1. Doesn't get much easier than that. We can't just do this with kilograms, though. We need to know how many moles we're actually talking about our various things. So we've done molar ratios. We did our balanced equation. We've done our molar ratios. Let's start talking about how many moles of each, though. Let's start with our AgNO3. I already did the work on the periodic table to get the mass of 1 mole of AgNO3. It's pretty massive stuff, in fact. How many moles of AgNO3 we have? Well, how much AgNO3 do we have per our problem? 250 kilograms. So 250 kilograms of AgNO3. That is the same as 250,000 grams. If you were confused about that, 250 kilograms. And then there's 1,000 grams in a kilogram, so just times that by 1,000, 250,000 grams. I have 250,000 grams of AgNO3, and each mole has a mass of 169.873 grams. So I'm going to divide that by 169.873, and that tells me that the amount of AgNO3 that I have going into this reaction is 1,471, how far do we want to take this? We'll say 1,471.69 moles. 1,471.69 moles. And then how much zinc do I have going into this reaction? I have, per the problem, 200 kilograms of zinc. So I want that in grams. 200 times 1,000, 200,000 grams of zinc. And each mole of zinc has a mass of 65.38 grams. So I'm going to divide 200,000 by 65.38. I have 3,059.04 moles of zinc. Okay, now on the other side of the reaction, we'll talk about that more later. But here's what I want you to notice right away. This is a 1-to-1 ratio. Part of my question is, what am I going to run out of first? And because it's 1-to-1, that's a really easy question to answer. I'm using equal parts AgNO3 and zinc. I have 3,059.04 moles of zinc and 1,471.69 moles of AgNO3. I'm going to run out of AgNO3 first. If you have 3,000 of something and 1,400 of something, 1,400 is the smaller number. I'm going to run out of AgNO3 first because it's a 1-to-1 and I only have 1,471 moles of AgNO3. So right off the bat here, we have one of our answers. My limiting factor is going to be AgNO3. I want you to notice something that's kind of fun about this problem. What did you have more of going in terms of mass? Did you have a greater mass of zinc or a greater mass of AgNO3? 250 kilograms of AgNO3, 200 kilograms of zinc. You had more AgNO3 by mass than you did by zinc. But in terms of molar quantities, you have more zinc than you do AgNO3. That's another illustration of why we can't use the ratios with mass. The ratios are for moles. Okay, we are going to run out of AgNO3 first. That is our limiting factor. The reaction is a 1-to-1. For every mole of AgNO3 that I put into the reaction, it reacts with 1 mole of zinc, and it produces 1 mole of silver and 1 mole of zinc NO3. So my ratio of AgNO3 to silver is 1-to-1. That means that my 1471.69 moles of AgNO3 is going to produce 1471.69 moles of Ag, silver, because it's a 1-to-1 ratio. One to one. I'm putting in this many moles of AgNO3, and I got that number by converting from mass to moles based on what the problem gave me and what the periodic table told us. And it tells me that I'm going to pump out that much silver before I run out of AgNO3. The last thing we have to do is answer the question in terms of mass. I can make that much silver, but how much mass is that going to be of silver? Well, if I look at what I've already looked up in my periodic table, every mole of silver has a mass of 107.868 grams. So 107.868 times the number of moles of silver that I have times 1471.69 gives us 158,748.2526 grams of silver. Now we're interested in kilogram. Well, you could give that as the answer, but it'd be a little easier writing kilograms. So let's divide that, the number of grams of silver, by 1,000, and we get 158 kg of Ag. Not bad. I wonder how much that would be worth. Let's see what Dr. Google tells us. You can see here, I don't always look things up on the periodic table. Just off the top of the internet, so who knows if it's true or not. $15.57 per ounce. There are 28 grams in an ounce, I believe. So let's see here. So $15.50 per ounce. How many ounces do I have? 158.75 times that by 1,000. That's how many grams we had. And then I said there's 28 grams in an ounce. So divide that by 28. That's how many ounces of silver, and it's $15.50 per ounce. $87,879 worth of silver came out of your mine. Good job. Good thing you figured out that reaction so that you could purify your silver, because it was in the form of useless AgNO3. Okay, we need boxes around those. We do still need to think about significant digits. Let's see what we were given. The problem gives us 3. In the problems, you assume significant digits for everything you have. So the problem is giving us 3 significant digits. I want to go ahead and turn this one into 3 significant digits. So we're going to say, we do our SDs. Throw a box around those, and we are good. Figure out your products and your reactants. Figure out a description of the reaction. Figure out your molar masses. Then use your ratios, because it's a balanced equation, to figure out which is your limiting factor based on how much you have by molar mass. And then make sure your answers are in the format stipulated by the problem. And you are good to go. I hope that was helpful. And one last thing, chemistry, real quick. I noticed as I was getting ready to close this out, I made a mistake in the problem. It did not impact the math at all in here, didn't impact the answer in any way, but there's something on this panel that's incorrect. Here's what we're going to do. If you can figure that out, I will add 5 percentage points to your test. So I like to reward you to think critically and pay attention to details, figure out the mistake on this panel, and we will add 5 percentage points to your test. God bless.